Hey there, friends, and welcome to another edition of our interview series. Today, we're joined by Professor Jeff Johnson, who is a professor in the geoscience department at Boise State University. I met Jeff just a few months ago. I took students to Boise State on a visit, and we got to tour some of the labs, and his was one of the labs we toured, and I was just really I guess, impressed with not just the kind of research he does, but also his ability to communicate really well. And then we ran into each other at a comedy show this last weekend. And so we've been putting together the schedule for doing this interview together. So, Jeff, thanks so much for taking time today. I appreciate it.
Thanks for inviting me to interview. Shawn, you didn't tell anyone what the comedy show was about.
Oh,
That's worth mentioning.
that's true. We went and saw a comedian that was doing a science comedy show, and I'm not really a comedy club fan per se. I just hadn't been to a lot of shows, but I thought I needed to go to this one, and it was fun. It was awesome. It was great. It was Ben Miller was the comedian, and he spent a month over in Hawaii Volcanoes National Park in their artist in residency program, and I guess worked on material, got to understand more about volcanoes and volcanologists and what people in the park do. And so, yeah, Jeff and I and our wives were there watching the show, and yeah, it was great. It was on volcanoes.
Yeah, I don't normally do comedy shows either, but this was it's a once in a lifetime opportunity with volcano humor. I had to go.
Yeah, I thought the same thing. Like, what are the chances I'm ever gonna, cross paths with a not just a science comedian, but one specifically focusing on volcanoes? And so I thought he did a great job. There was some funny stuff in there, and I thought it was the right blend of science and comedy together.
Yeah, and I quite like volcanoes, so it was
Yes,
appropriate for me.
I think we'll get into that. Yes, I think we're both volcano nerds on some level. So, well, maybe Jeff, we can start off with your a little bit about your background, where you grew up, how you got into science, maybe how those seeds were sown in you at a young or maybe not so young age.
Um, for sure, at a young age, I became interested in volcanoes, and I like sharing the story because I think it's relevant. I was 17 years old when I spent a school year abroad living in Ecuador. And Ecuador is a country that's full of volcanoes. At that point in time, they weren't very active, but there were a lot of high towering volcanoes that were super fun to explore. And so I spent a year learning Spanish, living with a family, going to a local high school, and also becoming a volcano climber. I ended up working with a climbing club out of Quito and had some very generous individuals who taught me how to use crampons, carry an ice axe. And in the process of that one year, when I was 17, turning to 18, I fell in love with climbing mountains and climbing volcanoes specifically.
So did you know at that point as a teen that this is what I'm going to pursue in college and further down the line, or was it more like a recreational hobby interest thing at that point?
Yeah, at that point in time, I was mostly just interested in having adventures, and mountains were definitely on my radar. I don't think I realized till later on in my undergraduate career that there was a possibility to do volcano science as a lifelong career trajectory. And so that's a long pathway. I'm sure many people know that, you don't just jump into being a professor. It's a long journey that goes from undergraduate to then graduate school, where other opportunities I can talk about became available to me. And then finally, I realized that I had a focus on volcano science that had some legs. I could carry it into novel research, and then I ended up doing the research science path, and eventually a tenure track professor
Right.
was where I ended up.
Well, before we get to some of your research, what I want to spend most of our time focusing on, let's go through. So you finished that year in Ecuador. You finished high school. Where did you go to college? Did you know right off you were going to go into science, and kind of talk us through those kind of college years?
Yeah, so I went to school in California in the Bay Area. I ended up thinking I was going to be a physics major because that sounded pretty cool and difficult, and it was difficult. Um, Maybe halfway through my undergraduate years, I took a geology class, went out into the field, and I said to myself, "Oh my gosh, if I could combine physics with going outdoors and exploring the earth and trying to figure out Earth history, and be camping and hiking at the same time. Wouldn't that be a great career?
Yeah, kind of like your outdoor recreational, passions combined with the science that you come to embrace, kind of putting those together.
Yeah, and I think many geoscientists have that pathway. They're in love with the natural world, and then they realize that geology, or in my case, geophysics, is a pathway towards being able to stay, to be to have a career that allows them to be in the natural environment. And in my case, that was what happened. The science was maybe not the priority in those early days, and it became the priority as I went into graduate school and I discovered how fascinating the life of a scientist can be and how much creative independence you can pursue as a scientist. But certainly the initial impetus for becoming a geoscientist was the love of the outdoors.
Right.
And I think that was born in Ecuador when I got to spend a year amongst towering volcanoes.
Yeah, what a great experience. Jeez, we could probably do a whole episode just on the Ecuador part of your life. So then were you did you go to grad school with a geophysics focus, or were you still kind of dabbling in both worlds? Like maybe just talk us through where you went to school and what those research projects looked like for you.
Right. So I've had, a few formative experiences, and one that's worth mentioning perhaps is at the end of my undergraduate career, trying to figure out what exactly I would do in graduate school. I knew I did want to pursue graduate studies in the geoscience world. I didn't know that it would necessarily be volcanoes, but at the end of my undergraduate days, I was invited on a field expedition to Pakistan
Oh, wow.
to do seismology, to study earthquakes in the Himalayas around Nanga Parbat, which is the ninth highest mountain in the world and a dramatic place to explore. And I had a professor from Lehigh University, Ann Meltzer, who was exceedingly bold in doing research overseas and especially in places like Pakistan. And I had the good fortune that she invited me to participate. So for 3 months, we installed seismometers all around the high Himalaya, retrieved data from those seismometers, interacted with local communities, had big adventure, and collected really cool data. So that was earthquake data.
Mm-hmm.
And I think at that point in time, I realized that there's so many opportunities to explore science. And if you're motivated and have the energy, you can basically decide what science is of interest to you, write grant proposals to answer questions, and then you get to, the only obligations that you actually have are that the community at large thinks your science is interesting. And then, of course, you do need to publish papers and demonstrate that you're getting results from the work.
Right.
So after Pakistan, I said to myself, I want to go to grad school and I want to study something that I'm very passionate about, which was volcanoes. And I ended up at University of Washington working with a professor named Steve Malone, who is a seismologist. He studies earthquakes, but he
Mm-hmm.
studied earthquakes at volcanoes. And he was the chief seismologist when Mount St. Helens erupted back in 1980. And so he was the head of the group that was locating earthquakes and trying to assess the unrest of that very important volcano in the lead up to its May 18th eruption.
Right.
I don't know if your viewers know there were about 2 months of precursory earthquakes prior to when Mount St. Helens
Yeah,
did its
along
big.
with ground deformation, I mean, as best they could quantify it back then. I mean, it was the techniques were definitely compared to today. I mean, you could speak to this. They were quite archaic compared to what we do today, but still, valuable. They still had the signs there. Is that fair?
Yeah, I mean, I love the first. It is, the first inkling that there was some volcanic unrest happening at Mount St. Helens was earthquakes, and then the deformation followed. But that first earthquake was something like a magnitude 4, and it appeared all across the Pacific Northwest seismographic network. It was an obvious earthquake. They didn't automatically locate it. The lab workers would take out the paper records and measure the times of arrivals. And according to Steve, they were guessing in those first few minutes where that earthquake might be occurring. And so there were a group of people with rulers and
Yeah.
calculators.
And yeah,
Uh,
compasses, yeah. Drawing
yeah,
circles, yeah.
exactly. Very old school.
Wow.
But by manual methods, they were able to say, hey, this is underneath Mount St. Helens. And then, the rest is history. There were a lot more earthquakes that happened. And 1980 was the dawn of this digital era where people were starting to use computers to automate earthquake locations and collect data using computers as opposed to just paper records.
Right.
So it
So
was an
your
interesting time.
yeah, your research with Professor Malone it was in centered on St. Helens and looking at the earthquakes there.
It began that way.
Okay.
So I arrived, bright-eyed and eager to engage in science. I had just graduated. Well, I took a year off between undergraduate and graduate school, which is advisable. I tell a lot of my students who are interested in graduate studies to, to take a bit of a break. It doesn't need to be a full year, but just breathe for a moment and then jump into your graduate studies. So I took that year off, went to Pakistan, like I said, and a few other places. And then I came in excited to do research. And I asked him, what could I do? I didn't know much about how to do research.
Right.
And he said, well, there's a question that's unanswered about Mount St. Helens and its eruption. And I've got this box of paper seismograms that maybe you can make sense of. It was seismic records from around Washington State and northern Oregon on the morning of May 18th, 1980, when that volcano erupted. And these seismograms had records of airwaves that had been radiated away from the volcano and had propagated, hundreds of kilometers to basically fly through the atmosphere and impinge upon the ground and shake the ground. So these seismograms
In the
were,
ground detected the air
yeah,
compressional wave basically.
yeah. So these are ground coupled airwaves from the eruption, and they were separate from the direct ground propagating seismic waves because they actually arrived later. Think about how seismic waves propagate through the ground. It's pretty fast.
Right. The P
They
waves get
go
there
at,
first, right?
yeah, there's the P waves, if you remember from, geology class or early geophysics classes. And then there are the S waves, and those travel, several kilometers per second. And then sound waves propagate at about a third of a kilometer per second, 340 meters per second. And these sound waves, it turned out, were flying way up into the atmosphere, turning in the stratosphere or even the thermosphere, 120 kilometers above the ground, and returning to Earth, where they were still strong enough to impinge upon the Earth, shake the ground, and the
Wow.
seismic sensors would pick it up.
So were they reflecting off of some layer in the atmosphere? Sorry to interrupt you. Like,
Yeah,
what directed them back down? Like some thermal
yeah.
layer up there, or
Exactly. Yeah.
okay,
So yeah, feel free to interrupt.
yeah.
I enjoy
This is
interrupting.
fascinating. Yeah.
We're going to use the word refract because
Okay.
there were no bounces or echoes off of layers in the atmosphere, so far as we know. But there were changes in temperature which caused sound waves to bend or to refract back to Earth. And this tends to happen where you have high temperatures in the atmosphere, and high temperatures means high sound speeds. And I know I'm getting overly wonky here, but in the stratosphere, 50 kilometers above Earth's surface, and then again in the thermosphere, where it gets really hot, 100 to 120 kilometers, you get sound waves that go up and then refract back down.
Interesting.
And they'll come back to Earth at reliable distances. And another interesting aspect for this eruption was no one heard Mount St. Helens erupt within about 50 kilometers. So it was this zone of silence, if you will, around the volcano. And then further away than 50 kilometers, out to 500 kilometers in British Columbia and Montana, Northern California, people reported hearing that volcano. Yet, if you're very close to it, it was silent.
So it
So
was
what's going on is these.
like a dead
Hmm?
zone, basically, right? Like a zone where a shadow zone, if you will, where the waves just weren't transmitted at all. Is that kind of the idea?
That's what we think. The shadow zone is the correct terminology. Yeah. So it was a donut of silence. Who knows what the sounds were like within about 10 kilometers of the volcano, because unfortunately people did perish in that sort of
Right.
immediate vicinity. But out to 50 kilometers, no one reported hearing it. And then further away, lots of people reported in. There was a collection of human perceptions of Mount St. Helens, what they heard across the Pacific Northwest, and people responded to a poll back in 90 and reported hearing thunder and barrages of what sounded like gunshots or booms. Um, and then at the same time, these sound waves were also reaching the ground and shaking seismometers. So
So were those coming in after the S waves? I'm wondering how you picked apart the sound waves on the
mhm.
seismograms when you have all the seismic waves themselves. Like, were they a clear set of waves after the surface waves?
Yeah, indeed. As you can imagine, a big eruption like Mount St. Helens is going to generate seismic waves as well as sound waves. And those seismic waves, they travel so quickly away from the volcano that many of them had sort of dissipated, had come and gone, and then the sound waves come in later. There's also an interesting peculiarity in that the seismic waves are high amplitude, fairly close to the volcano, but they tend to fall off in terms of their amplitude at greater distances.
Mm-hmm.
Um, so suffice to say that a seismometer a couple hundred kilometers away from Mount St. Helens did not pick up the earthquakes as clearly as those that were closer, but they did effectively pick up the sound waves.
Hmm. So do the sound waves not dissipate as much with distance as the seismic waves themselves?
Yeah, I think that's part of it. I think if you can envision what's going on with that sound radiation, it's not necessarily geometrically spreading into a half space, but it's going out as an annulus, as a ring.
Mm-hmm.
And so it maintains its amplitude. To first order, it maintains its amplitude pretty decently. And then there's the other aspect of it, which is infrasound doesn't dissipate due to absorption of the medium itself. So infrasound, which
Mm.
is low frequency sounds, and I know we're going to talk about infrasound
Yeah.
shortly, um, tends to propagate long distances without attenuating. And that's
Wow.
one of the things about it. You can record infrasound from volcanoes, in fact, globally, if the eruption is big enough. Um,
Wow. So
so we
really, yeah, really great tool there because you can, again, it doesn't attenuate, so it travels around the globe essentially.
It can for, I think we're gonna mention Hunga Tonga in a moment, and we can talk about Krakatau. Those were the big eruptions that propagated sounds globally, and not just globally, but the sounds propagated around the Earth multiple times. And those were low frequency sounds. I don't recall hearing the Hunga Tonga eruption, which happened 2 years ago
Mm-hmm.
in January. Yet the specialized microphones that we're going to be talking about located globally picked up that big eruption.
Wow.
Um, and so let, let me just add that Mount St. Helens work that was early in my career sort of stimulated this interest in, hey, maybe we shouldn't be listening to volcano sound waves using seismometers. Maybe we should be using the proper tool, which I think is the infrasonic microphones. Not
Right.
just normal microphones, but infrasonic microphones.
So that research, your graduate research, kind of set the stage for the rest of your career. It sounds like. I mean, that really kind of was the stimulus that got you interested in this world of infrasound.
Yes, in fact, so after that first project, and I should add that Mount St. Helens research was just the start of my graduate studies, but I became interested in sound through that process, and those were the early days of volcano. We'll call this volcano acoustics, which broadly means volcano sounds.
Mm-hmm.
And there had been work that had been done, but there wasn't a large community at that point. So I like to think I was very privileged to be involved in an area of volcano research that was just starting off. Um,
Yeah, on the front lines. That's awesome.
and I was asked to participate in a field project as a graduate student in Kamchatka. You know where Kamchatka is?
Yeah, Northeast Russia. Yeah, across from Alaska.
What do you know about Kamchatka?
It's a subduction zone. It's a big peninsula there, but lots of stratovolcanoes. That's all I
Yeah.
know.
Yeah. So 20% of Pacific Rim Holocene volcanism comes out of this little knot of mountains in Kamchatka, and
Wow.
it's extraordinary. It's a really active place in terms of volcanology. And I was invited to go to an active volcano there, my first active volcano as a graduate student.
Wow.
And,
Yeah, talk about
and
that experience just for a few minutes. That
Mhm.
sounds like that was probably quite the experience.
Yeah. So shout out to Professor Jonathan Lees from University of North Carolina, Chapel Hill. And, he met me and knew that I spoke Russian, which was a high school interest of mine, and that I had been to the Soviet Union. So that dates me a little bit. I was in the Soviet Union for 3 months during its last year. And then he was in charge of a project in Kamchatka, again, an earthquake project, but he said, there's an active volcano there. And there's this thing called infrasound. Have you heard of infrasound, Jeff? And I said, yeah, it's volcano sounds. It's pretty cool. So Jonathan said, all right, if you can build a sensor, I'll pay for you to come out into the field with me. And so I asked very nicely to our tech people at the University of Washington, where I was doing my grad studies, if we could put together an infrasonic microphone and I could go out into the field with Jonathan in Kamchatka. And it was a life-changing experience um, because, well, Kamchatka is an exotic place, a lot of active volcanoes, big, gnarly brown bears, and
Bad weather.
bad weather, interesting people. I mean, volcano scientists who know a lot about um, the field and are also old school in some ways. So there are some really incredible personalities, people I learned a lot from. And we got a chance to work at Karimsky Volcano, which
Yeah.
is one of these. Have you heard of Karimsky?
Yeah, that's one of the ones I know. Yeah, I've heard of. I don't know much about it. Just it's active. It's more active than some of the other ones, I suppose.
Yeah, yeah. It's got a fascinating story with a caldera, an eruption that was synchronous in the nearby Caldera Lake called Academia Nauk, and I think that was 1996. And then the stratovolcano itself, which was active at the same time. And so by the time we visited Kamchatka, it was only the stratovolcano that was doing its thing, and it was popping off with regular explosions every 10 to 15 minutes. And I had never seen anything like that in my life. I mean, you land in a helicopter in the middle of nowhere, Kamchatka, and then you look up and there's this cone, this volcanic edifice
Mm-hmm.
that has stuff coming out of the top of it. Every 10 to 15 minutes, this boiling cloud of ash and gas and is rising up, and you can see these ballistics from 3 kilometers away.
Yeah.
And a ballistic is a volcanic bomb, and they're arcing into the sky, and then they're hitting the slopes, and they're rolling down the slopes and kicking up these contrails of ash. I mean,
Wow.
it's mind blowing. And then at night, these explosions, those bombs are incandescent, right?
Yeah.
So,
Yeah. So
you
then you
know,
get the
it, it,
fireworks. Yeah.
it's fireworks. And so this was a fascinating opportunity, and I was able to put out my infrasound sensors, and I'll learn a little bit about doing volcano field work in an active volcanic environment. And so I spent
Wow.
3 seasons working there.
Fascinating. Wow. Well, since we've mentioned it already, maybe back up and explain to the viewers and myself what is infrasound and how does it, or just sort of the science of sound, I suppose, and what the difference is between infrasound. There's things called like ultrasound. There's
Mhm.
the sound waves we hear. Maybe just give us a little primer on that.
Great. I'm glad you asked this question. So ultrasound is high frequencies, and that's what bats do to echolocate. So far as I know, no one has done any ultrasound studies at volcanoes, at least not active ultrasound emissions. Uh, Ultrasounds have high frequencies above the threshold of human hearing. That means more than 20,000 hertz. And we're not sensitive to ultrasound. And we're also not sensitive to infrasound, which is below 20 hertz. A good rule of thumb is that big things like volcanoes or earthquakes or other earth phenomena produce infrasound, whereas small things tend to produce
Hmm.
ultrasound.
Okay. Yeah.
So a lot of geophysical events, including volcanoes, produce prodigious infrasound. We can't hear it. It's below the threshold of human hearing, but it doesn't mean it doesn't exist. We're just not sensitive to it. And there's this world of sound bombarding us right now that we can't perceive, but if we have the right sensors, we can listen to it.
So you just
So human.
make sensors that detect those frequencies, right? That's
Mhm.
basically the game is just changing the range or the threshold of frequencies that the sensor picks up. Sounds like it's pretty simple. Is it as simple as that?
It really is. And the sensors are not like space age sensors at all. They're pressure transducers. And we do a few clever things. I would say they're clever. Someone else might say it's not so clever, but we do a few things to try to optimize the response of our infrasound sensors. They are calibrated scientific instruments. That means we can actually turn the signals we record into pressure amplitudes, and we measure those in pascals. We also know what the response of those sensors are, such that we can use the waveforms recorded to do physical modeling. But the other important thing is that we need to throw away this entire world of barometric changes. Um, so, and yeah, and more than just barometric changes, but there's this whole world of pressure oscillations that humans just don't hear. You might be aware of them because low pressures and high pressures come in all the time, and they're associated with weather. But we're
Right.
not interested in that when we're studying volcanoes.
And
So
you
we
can,
do filter.
yeah,
Yeah.
I was going to ask that. Yeah, you can filter those out and make sure those aren't affecting your data.
hmm Yeah. So again, to get a little nerdy here, what we try to do is we try to focus on the sweet spot above zero point 0.1 hertz, which is a 10-second period, up to about 50 hertz, which is extending into the audible band. And so
Hmm.
that is the zone where volcanoes like to speak with the most amount of energy.
So you're saying that the volcano makes more sound in the infrasound range of frequencies than anything we actually hear if we were to just sit there and listen, like you said, in Kamchatka, at this active volcano. Because I've been at some eruptions too, and like the audio component is incredible, like the sounds, the
Mhm.
the pulsating jet noise. But you're saying in the infrasound range, if you could hear at that in those frequencies, it would be a cacophony of sounds, and it would be much more rich in terms of what you'd hear.
It would definitely be distracting and loud and maybe scary as well. So, and if those sounds are intense enough, you can feel them, just not with your ears. I mean, I've been in situations where I've felt unease in sort of my chest cavity because the infrasound is so intense that it's actually giving a pressure sensation on non-auditory components of my body. Um,
Wow, almost like a very strong like subwoofer or something. Like, is that sort of an analogy where you're like, the car rolls by your house with the bass really thumping, and you can kind of feel that in your body a bit.
exactly.
Okay.
And so, actually, this is an interesting side note. But a few years ago, I had the opportunity to take an actor, Will Smith,
Mm-hmm.
to an active volcano as part of a documentary. And the show is called Welcome to Earth on Disney National Geographic. And I was pleased to be able to show off the science of infrasound to Will Smith and also to an individual named Eric Weinmeier. And Eric
Yeah.
is a non-sighted adventurer, explorer. He's climbed Mount Everest. Some of your listeners might know of
Yeah,
him.
he's kayaked big rivers, he's skied big hills, and yeah, I know the name. He's an impressive person.
Yeah, he's my role model. Yeah, he changed my life. And he was involved in that project because specifically we were at an island volcano in the South Pacific called Yazur, well known for its active activity, its frequent activity, it's continuously erupting, exploding, and it's a great place to study infrasound. So Eric was with us and was commenting on the sensations that he perceived from this volcano, um, that were non visual.
Right.
He could hear sounds. He has an incredible sense of hearing, but he's also in tune with other maybe other components of his body that can sense these pressure fluctuations. And so he was commenting that this volcano was producing sounds that he was aware of that my sensors could detect, but I
Yeah.
couldn't necessarily make sense.
That's impressive. So, I mean, given the right conditions, humans could, quote unquote, hear or feel at least some of these maybe infrasound frequencies. People like him that have other heightened senses. That's
Hmm.
kind of neat, kind of promising in terms of what humans, are capable of. Obviously, they're not hearing all the or feeling all the infrasound frequencies, but maybe some.
Yeah. There's also animals that can sense infrasound down to, different ranges, elephants most notably, but some animals may even migrate, like migratory birds can use infrasound in theory to um, help navigate. They're actually listening to the infrasound associated with what we think are ocean waves.
Mm-hmm.
So there's this background of ocean wave, we call it microbarometer signals, that as a volcanologist, it's noise and I don't like it. But if you're a bird, you can listen to that microbarometer and figure out that, oh, yeah, the ocean is off in a certain direction and
Right.
maybe use it to navigate with.
So, what about infrasound? Obviously, when a volcano is active and erupting, you're hearing things, or maybe hearing's the wrong word, but you're detecting that infrasound with your instruments. Is there something to infrasound that will help us with not prediction, but maybe monitoring volcanoes and seeing what they might do when they're not active, or the signals they give us when they're not erupting visually that we can see, but magma's on the move and maybe something's going to take place in the near future?
Right. This is the $1 million question is your science actually applied in any way, or is it, just
Yeah,
is
fun.
it an intellectual curiosity or is it useful? And I like to think that my science can be applied. And in fact, we've demonstrated this on a couple occasions. Um, right. So, early days, I was using infrasound to try to understand the dynamics of an eruption. Maybe we could use these signals to figure out how much um, gas was being exploded during an eruption. And we did a lot of work sort of to infer source processes up there on the volcanic vent
Mm-hmm.
when you can't see the vent, can you infer how much gas was exploded? And so yeah, we were able to do that sort of thing. And then subsequently, after many years and many volcanoes collecting infrasounds, we came across a few examples where infrasound monitoring, we think, is capable of forecasting certain types of eruptive activity. So I can share one example of that I'm particularly proud of. It's a volcano in Chile called Villarrica, and it's a beautiful volcano. It looks a bit like Fuji, a kind of a classic volcanic shape. It's mantled in glacier. The top has a narrow but very steep walled summit crater that goes down into a lava lake.
Mm-hmm.
That's a permanent lava lake, or 90% of the time the lava lake is there. And so that's a boiling pool of molten lava that is degassing all the time vigorously. And this volcano is perpetually active. We call it an open vent volcano, but every once in a while it erupts paroxysmally, which means it has a bigger
Yeah,
eruption.
more explosive. Yeah.
10 years ago, and now it's what, March 7th? 10 years and 4 days ago, it erupted paroxysmally. And I was in Chile living at the time at the base of the volcano. So
Wow.
I had this project that serendipitously coincided with the paroxysm. And I was doing this esoteric infrasound work where I would put sensors at the top of the volcano and all around the base to try to understand how sound would propagate away from the volcano and understand the attenuation and other um, let's just say sciencey type objectives. But it turned out shortly after we installed our sensors in the top, the volcano starts waking up and starts erupting a little bit more violently. It's throwing rocks up and out over the crater rim. They close the volcano to climbing because they don't want, anyone to get hurt up in the
Right.
crater rim. There's a lot of tourism. And so that continues for a few weeks, more than a month, in fact, until the very end of February. At the end of February, the activity is ramping up a little bit more, but it's not noticeable, except that in the infrasound records, what we're observing is the frequency content of these explosions that are happening every few minutes is changing. It's becoming higher and higher frequency over the course of, let's say, 72 hours. And also, those signals they have a waveform that's different. prior to the end of February, those waveforms would have a resonance associated with them. So if you look at the explosion, you would see it kind of like vibrates a little bit. And then in early March, that resonance goes away, the frequency is climbing, and on March 3rd, it erupted paroxysmally.
Hmm.
So I wouldn't say that we were able to forecast the eruption, but after the fact, forensically, we looked at our data and we said, oh, we are observing the rise of this lava lake within the volcano.
Hmm.
Okay. And rising lava lake is basically shortening our pipe that's available for sound resonance. And we're observing a lava lake that's systematically rising within the crater.
So do you think the signal you were seeing was increased gas coming up through the system, and that's why the lava lake was rising? Because you said it was a different waveform, so I'm wondering how you interpreted that waveform.
Yeah. Can I show you some visuals from this volcano? I
Yes,
think this would be
absolutely. Let's
useful.
let's do that.
Okay.
Let's see.
Uh,
Are
I
you
think I need to request sharing permission.
okay? Yep. Should be good to go now.
Okay. And now let me know if you can see this
Yep.
well enough.
Yep, I
All right.
do. Looks good.
Oh,
So that's
okay.
looking down into the crater there, it looks like maybe?
Yeah, let's back up just a little bit here. So I mentioned already that Virica is this gorgeous volcano. Let me make it full screen.
Perfect.
Can you still see fairly well?
Yeah, that looks great. Thank you.
Okay, so there's that white glacier-covered volcano in the back, and you can just see a little bit of fume coming out of it.
Mm-hmm.
And the reason we love to study Villarrica is because it's one of these few volcanoes that's open vent all the time and continuously produces infrasound all the time. Really loud infrasound. Um, and so, we put sensors on the top and then around the volcano. In fact, I think Eureka's infrasound is, oops, I want to turn off the audio on this, or maybe I'll just forward it manually. Okay, so you can see looking down into the crater. I hope this is registering fairly well.
Is this with the
That
drone? I'm wondering how you got. Sorry, I got to ask how you got these visuals as we're watching this.
Yes.
Okay.
So I fell in love with drones about 10 years ago when they were first available for consumers. And that's another topic of conversation
Okay.
that maybe we can have, Shawn. But oh my gosh, it's changed the life of volcanology. And we
Oh,
do
for
all
sure.
sorts of cool things with drones. Like this, we make these beautiful maps that we could never have done before without having, a huge expense account.
Right.
And so, flying over the volcano and making maps of the crater is part of the story. And what I'm showing you right now, without getting into too many details, is the concept of the lava lake indicated by this blue
Mm-hmm.
column rising up in the crater over time, over a couple days. And this is what we've modeled. So geophysicists love to model phenomena. We record signals, and in this case, we were recording infrasound, and we attributed it to a certain shape of the crater. Does that
Hmm.
make sense?
Yeah.
Like,
Yeah.
if we
The
have
the, the
high,
the geometry of the crater in terms of its symmetry, how steep it is, how wide it is. That the
yeah,
idea?
yeah, and we actually borrowed from the world of instrument brass horn acoustics. If you
Yeah.
think about a trombone with a shortening tube length, you can change its pitch or its frequency.
Mm-hmm.
Uh, and so we were using this model of a pipe with a funnel on top of it to replicate certain sounds. And we knew what the geometry of the crater was, but we didn't know where the lava lake was. So we modeled the height of the lava lake as it changed over time to give us our sound results. And
Hmm.
as soon as the lava lake rose up to the shallow parts of the crater where it starts to funnel, all hell breaks loose. At that point in time, what we think is happening is you're able to slosh lava magma over the crater rim. You're able to unweight the
Yeah.
column of
Pre-
lava.
Pressure decrease. Yep.
Yeah, the exsolution sort of ramps up. It's a feedback. I think it's a feedback process, positive feedback process where you have a runaway eruption.
Yeah. Kind of like a
Uh,
geyser, really, in a way.
yeah, yeah, I think there are parallels.
Yeah.
Certainly, there was elevated there was elevated gas flux that was occurring during January, February, March of 2015. But once this process runs away, then you get this column of lava that erupts like uncorking a champagne bottle. And what you can see here is shortly after the eruption started, a still image that is a kilometer and a half high, so a mile
Wow.
high column of lava, dramatic, especially for those of us living in town. And I was
Yeah.
there with my family.
And it was at night
Well,
when it erupted, huh? What was
yeah,
the time component between when the lava lake was rising and you were seeing those signals and when the peak of the eruption occurred?
yes. So looking back at the data, I wish I could have said, we were monitoring this thing in real time and we were aware of what was going to happen. That's not how science always works.
Yeah.
Sometimes you look at the data afterwards and you say, oh, wow, there's the signal here that we didn't recognize.
Yeah.
So that signal of interest started literally the last hours of February, and then 3 days later, March 3rd, the big eruption happened.
Okay.
So that's a substantial amount of time. You can, in theory, let people know that there's elevated risk of eruption. Um, and then the eruption lasted, believe it or not, only a half an hour. It
Really?
it it
Wow.
was really brief, and then it was over.
And
And
where
the
was the
last,
lava lake after the eruption? Was it back down to sort of the original pre-rise level, more or less?
even lower, it
Okay.
had disappeared entirely. Actually, it was interesting because if the overflights on the next day showed a volcano that had appeared to be sealed up near its top level, but that belied a void within the conduit that was empty space. So
Right.
within just a few days, that collapsed in on itself, and then the lava lake was nowhere to be seen. It was,
Way deep. Yeah. Yeah.
and it did recover in several months. It came back to its equilibrium level, which is about 100 meters below the crater rim. But right after the big eruption, it was lower.
Wow. Fascinating. Yeah. So that just being able to see those pressure changes and what a cool approach, like modeling it after like a horn, just like, well, this is a volcano, it's an acoustic instrument, and so if you've got the length of the conduit, if you can just look at the geometry like you said, then you can actually kind of match that up to your data and make some conclusions there.
You should ask me what happened to the sensors that were on the summit of the volcano.
Yes, we of course would like to know what happened to those.
We never got them back. They are long gone. They were encased or entombed in lava, and they disappeared. So those data were gone.
Those were on the rim or actually down in the crater a bit.
They were on the crater rim, and nothing survived on the crater rim.
Right.
Which is the local Chilean monitoring agency that I work with from time to time, they lost a bunch of infrastructure that was on the crater rim as well. Um, the price to be paid. Fortunately, we had infrasound sensors located all around the volcano at safe distances, as close as 4 kilometers and as far away as 30 kilometers. And so the entire record of that eruption was preserved with sensors that were further away.
Wow. Yeah, imagine doing this type of work. You lose sensors and instruments from time to time. It's the price of doing business, I suppose.
It is, although, as an academic, all of the hardware is so dear. We're not especially flush with research dollars, so
Right.
we care for our instrumentation very
Yes.
carefully,
It stings
and
when you lose it, probably,
it
no matter
hurts.
what. Yes.
Um, but
Hmm.
this was a once in a lifetime, I would say, eruptive sequence where it went from quiet to very violent. And I should add that Eureka only erupts like this, every 30 years or so. So
Yeah, good
um,
timing. Yeah.
my Chilean colleagues were somewhat, um, I don't want to use the word jealous, but they marveled that I had sort of been able to swoop in and during a 5 month period living in Chile, captured an entire paroxysmal event,
Yeah,
which,
like you landed in the plane on the you got there, you put your instruments down, and then within a pretty short period of time you got a nice eruption and all the data, most of the data anyway. That's probably
yes,
about as good as it gets.
I was lucky. Yeah, for sure.
Um, Well, do you have some? Do you want to? You have the Hunga Tonga one there. Do you want to just go right to that? That's as good a place as any to talk about this, I suppose.
Yeah, so while we're on sharing screens, I figured I might as well just transition over to this video. So maybe a bit of background. I'm a stamp collector, but not, traditional stamps, but volcano stamps. I like to collect signals from volcanoes. And so I've been fortunate in my career to get to do a lot of field work. And infrasound is one of these fields where collecting signals from different volcanoes helps us to understand, well, the variety of volcanic activities and do comparative studies. So I almost never say no to doing field work on active volcanoes, but very occasionally you don't even need to go very far to collect infrasound from volcanoes. The infrasound may come to you. So I mentioned earlier that there was a big eruption that occurred, I believe it was January 14th or 15th of 2022. Do you remember that eruption,
Yes,
Shawn?
yeah, I did a video on it because I didn't, know much about that, but it was big in the news, and all we had to go on here, at least some of the things I found was the satellite imagery. You could see the plume, and this was a undersea volcano that had erupted through the ocean from the ocean floor to the surface and had produced a big cloud of ash, but also apparently an infrasound wave and maybe an acoustic wave too.
Mhm. Yeah, let's just say it produced a lot of atmospheric pressure waves of various forms. The, the pressure waves we're most familiar with are sound waves, but there are also things called acoustic gravity waves and Lamb waves, and these are all pressure waves that happen in the atmosphere that physics predicts and were produced by this giant eruption of Hunga Tonga. Um, you said you did a show on Hunga Tonga eruption not too long
I
ago,
mean,
or
in the
a year
moment,
ago.
I did just kind of like letting
Yeah.
people know as what little bit of science I could share with it. I think I read later it was VEI 5 maybe, and so it was maybe one of the biggest eruptions on the planet in the last, I don't know, like maybe 30 years or so, whatever the numbers
Yeah.
are, but impressive.
So I was hoping you'd mention its size because I've seen estimates of VI6 for Hunga Tonga. And just to remind your listeners, a VI5, Mount St. Helens 1980 was barely a VI5. So VI6 eruptions happen once a century, maybe twice a century. They're uncommon. And this was the biggest eruption to have occurred in quite some time. It was bigger than Pinatubo, um, which is 1991.
In the
And it
Philippines.
was, yeah, it was remarkable. It was also similar in some ways to Krakatoa in terms of its size, which was 1883. Am I getting
Hmm.
that
Yep.
right?
Yeah. Good job.
Um, which was previously credited. People like to say it was the loudest sound ever produced on Earth, and by certain metrics, that's the case. Hunga Tonga is a close second, if not similar. And so, what I'm going to show you right now is the sound, okay, not the sound, but the airwave signal that was recorded in Idaho, which is where I live. And we weren't listening to volcanoes here in Idaho. Uh, that's just not, that wasn't on our radar back in 2022. We were deploying these infrasound sensors to listen to snow avalanches in central Idaho up in the mountains. That's another story altogether. But they were out there recording, continuously listening for events of interest from the local snow avalanche activity. And then there was this event that happened 10,000 kilometers away. So I will just play this video and hopefully there's not too much stuff cluttering my desktop. But what you'll see in a second is the eruption as viewed with satellite imagery. And then something like 8 hours later, you can see the red time bar marching across the
Hmm.
screen. That's basically a very sped up version of the sound waves
Yeah, and there
that's
was a little
being
thump there when it hit
recorded.
that first big high amplitude section that I heard.
Yeah, so I've
Okay.
actually sped up these waveforms so that they're in the audible band. But all told, what you can see here is there is a primary pulse. I'll play this one more time. That's occurring shortly after move this forward in time. Right around here, if you can see that red bar,
Mm-hmm.
that's the first arrival of airwaves from Hunga Tonga traveling 10,000 kilometers
Wow.
and arriving 8 hours after the eruption in Idaho. And
Wow.
these sensors are buried in the snow up near Stanley, Idaho, and they're picking up a 6 Pascal signal. That's pretty substantial sound pressure amplitude. And it was the first time that I recorded a sort of a global signal on Idaho infrasound sensors.
No, that's crazy. You picked up a signal under the snow from a volcano half a world away that erupted under the ocean. Like, I mean, if you just keep adding all the little qualifiers there, it's pretty
Mhm.
incredible. I'm assuming infrasound detectors that were at the surface picked it up well and maybe picked it up a little more clearly, or
Yeah, in fact, it was buried in the snow, but we can almost consider that to be nothing more than a little bit of a muffle on top of our sensors. We're listening to such low frequencies that the snow is almost transparent to these sounds.
hmm,
As
interesting.
long as you're not encased in an ice cube,
Right,
these infrared sensors in a porous snowpack will hear things.
right.
In fact, yeah, everything you said was, I think, is remarkable. I'm glad that you're also excited by it.
I think that's really
Um,
cool.
but see that second pulse coming in right now?
Yeah,
You
just
see where the
behind the
red
red
line?
line. Yeah. What's
Yeah.
that?
I wonder if you can tell me what's going on there. So as a hint, we had a direct arrival, take 8 hours to travel from Hunga Tonga in the South Pacific to Idaho. What's
Those
going on here? There's
those are
another packet.
probably the actual seismic waves, I would guess, that have finally come in. Is that true?
N Not seismic waves, because the
Oh,
seismic waves are going to travel
oh, that's
faster.
true. Those will be fat. They're faster.
Yeah.
So,
It takes 20 minutes for seismic waves from a big earthquake to travel all the way across the globe.
right.
The first arrival of the sound is taking 8 hours. And so this is coming in 27 hours later.
Oh, it's gone all the way around the planet and come back again. It's a second, uh, just circumnavigation of the globe, if you will.
Yeah, I
That's
think that this second arrival here is sound that's going the wrong way around the globe. It's traveling not from the South Pacific northeast towards us, but it's going
oh, for the other
to
way.
Africa and
Yeah.
the other way.
Okay.
So we hear it and we see it, and then there's a third pulse of energy, and this is your circumnavigation.
Okay.
We're at 48 hours now. So it takes about 40 hours for airwaves to circumnavigate the globe.
That's crazy. And I'm assuming like the wave form of these things looks totally different than the avalanches your infrasounds were trying to detect. I mean, in terms of amplitude and like the shape of the waves, is that true? Like there are different signals?
Yeah, yeah. And so what you're seeing here is a uniquely large eruption, and the low frequencies from this eruption, meaning well below 1 hertz, are what's perhaps most impressive. And so I'm not going to call this infrasound. I'm going to just call it atmospheric pressure waves because they
Mm-hmm.
belong to a different type of or family of airwave that's propagating around. Think of this, if you will, as maybe more like um, uh, ocean waves or ripples on a pond. The atmosphere is being disrupted and it's having these ripples emanate outward from the eruption.
Right.
And so that's a different propagation mechanism than pure sound waves. But the speed is fairly similar, let's just say.
Is it analogous to, I don't even know if this is right, but I have seen videos of like a boat offshore of Krakatoa, or not even Krakatoa, but a Nat Krakatoa, the small one that's left behind, and there's a small eruption at the summit. You see it, and then on the boat, this video is all over YouTube. You might have seen it too. I guess the acoustic pressure wave or whatever the right word is comes through, and it's like it essentially is breaking the speed of sound. It's like the pressure wave is so fast and high amplitude that it actually moves at that speed. Maybe walk us through the science of what I saw there and getting it right.
Yeah, I like that. I'm gonna actually find another video for you to show that phenomena that you're describing, and I think your viewers might be able to visualize this a little bit better. Um, I would like to share again. Okay, and I think I'm gonna try to make this bigger. Oh, after all these years of using Zoom, I still struggle sometimes.
Well, now
Okay.
for me, I'm using it so less frequently that it's like reminding myself how to use it every time. Like
Mhm.
learning curve.
Okay, so we're talking about a lot of things, trying to focus ourselves now. You were mentioning the fact that sound waves are so intense, or infrasound waves can be so intense that you can actually visualize this shock wave. I'm showing you yet another volcano. This is actually Yazur in the South Pacific that has these small explosions for which we can see pressure waves. If you look closely, you might have seen a shock wave propagating through the cloud. And so what I like to do is record infrasound, which is this red waveform that you're seeing in real time, an explosion. And if you look very closely, you
Yeah, on
might
the
see
left there, I
cloud.
saw something.
Mhm. And so one of the things I love to do, and this is not the best video, is I love to look at video and try to pull out information from video. And so this one is the video I had hoped to show you. And what you can see in slow motion is that same
Oh,
explosion
wow. Look at that.
and image enhancement showing these sound waves propagating through the cloud. And what we're doing is we're optically recording the infrasound.
So there were several pulses there, it looked like maybe 4 or 5. Is that right?
Mhm. Remember early on when I talked about Eureka, I suggested that the frequency was changing as well as this thing called the resonance of the sound
Mm-hmm.
waves. Um, this resonance is particular to each crater that we have studied. In fact, if you have a long, skinny, thin crater deep, it will have a very pronounced resonance, whereas if it's funnel shaped and open, it won't resonate hardly at all. Think about the trombone example.
Right.
And so you're seeing some crater resonance there.
Wow.
Uh,
So it's like it's amplification through resonance of the initial wave.
yeah, you're exciting a resonant mode of this natural system that's a musical instrument, a
Mm-hmm.
giant musical instrument.
Wow, that is cool. Yeah, you could really see that moving through there. So that,
Yeah. But
whether it's infrasound or audible sound, I mean the physics is the same, right? If it's resonance, then you're going to
mm,
still get that same kind of characteristic.
yeah, and I think that's the important thing, take home message here is, humans have their filters which allow us to see certain wavelengths of light or listen to certain sound wavelengths, but there's this world of radiation around us that we can't perceive.
Right.
And geophysicists are able to make use of this world and other scientists because we develop sensors that can measure these things that humans can't sense. But this radiation is all around us, and it's fascinating, and it allows us to understand physical processes of the Earth. Um, so infrasound for me is sort of the tool that I've been able to take advantage of to listen to Earth processes. And I don't know how much time we have left, but I can spend just a moment or two talking about things that we do with infrasound beyond the realm of volcanoes.
Yeah, go ahead.
Uh,
We're good. I'd like to hear
yeah,
that. Yep.
yeah. I think you actually did ask a question about it earlier, and then we got sidetracked, or I got sidetracked. Um, I mentioned that big geophysical sources, earthquakes, volcanoes, debris flows, snow avalanches, big things tend to produce long wavelengths, and long wavelengths in the world of sound is infrasound.
Mm-hmm.
Um, so while my first love was volcanoes and infrasound produced by volcanoes, I realized that there is a lot of interesting science to be done in the world of infrasound outside of volcanoes. And Villarrica, a volcano that we talked about at length already, is a great example of a place where infrasound doesn't just come from the crater. During that paroxysmal eruption back in 2015, there was a lahar
Mm.
that was produced by that eruption. Do you know what a lahar is, Shawn? I'm
Yeah,
sure you do.
volcanic mud flow. Yeah.
Mhm. And so using our sensor network from Villarrica, yeah, we recorded that explosion, but after the eruption ended, 30 minutes later, there was this 3 hour long signal that was coming not from the volcano summit, but it was coming from the flanks of the volcano. Moreover, that source was moving away from the volcano. And we could tell this because we put out multiple sensors and we could track the movement of that source. And it was propagating down the flanks of the volcano and out to distances maybe like 20 kilometers away from the volcano. And it coincided with what we came to find out. There was a mud flow, a lahar that came down the volcano that night. It happened under the cover of night. No one saw it. It took out a couple bridges. It didn't hurt anyone. It could have been disastrous, but it was sort of a medium-sized lahar, and we were
Hmm.
able to track it with our
Wow.
infrasound sensors.
So you can actually see the Lahar in real time. Can you see it like moving down the flank, like its position and its speed? You can figure that out.
Yeah, I have another video that I won't be able to find right away, but it shows it's the progression of the Lahar sound source moving down the volcano.
Hmm.
Now, it's important to mention that none of these sensors at Villarrica were relayed and analyzed in real time 10 years ago, but the science that we were able to extract from those experiences is now being utilized by volcano observatories to do real-time tracking of hazards.
Hmm.
Um, but what we learned 10 years ago from that lahar at Villarrica is that the moving source of sound, which we now know is a lahar, was moving down the slope at 38 meters per second.
Wow.
Okay.
Well, that's pretty fast. And I mean, it kind of makes sense because you have these very steep slopes on the flanks of this thing.
Mhm.
And in maybe a channel without a lot of obstructions and stuff, you could get some of those velocities. Was the Lahar just a simple? You just melted some of the snow and ice at the summit during that eruption with some of that lava, and that was the trigger of water.
I think that's a great hypothesis. I can't answer that absolutely, but there was a lot of hot scoria that was landing on the
Mm,
glacier, incandescent rock, ice. Could it have been an outburst of some water reservoir under the ice
yeah,
that was triggered by that eruption as well? Yes. I don't know, is the answer to your
right.
question. But I do know that whatever was moving was trucking along at a really fast speed.
That's
And
incredible.
I love the metric system, but I still have to convert 38 meters per second to, you know, miles per hour. That's like 80 miles per hour.
Yeah.
So a mud flow racing down the volcano at that speed is terrifying. Um,
Well, and you'd think it
and
would have like turbulent flow and like there'd be enough, even though it's steep, there's enough sort of friction and obstacles that it would maybe slow it down a little bit. But maybe, I don't know if it's a scoured out channel. It's been a lot on the channel dynamics and the viscosity of the Lahar, like lots of factors.
yeah, and since that observation, we've continued to study lahars from volcanoes using infrasound. And yeah, maybe we're getting close to our end, but one of the cool areas of research that I've been pursuing recently is trying to use these technologies to track in real time the lahars that are occurring at volcanoes like Fuego volcano in Guatemala. I don't know what you know about Fuego, but do you know anything about Fuego?
Yeah, I mean, subduction zone, stratovolcano, constantly active. I think usually there's lava flows up near the summit. If that's the one I'm thinking of. Yeah, I haven't been to that one though.
Yeah, it's a very hazardous volcano because it's got so many people living on its slopes. It deposits a lot of unconsolidated material on the upper slopes that tends to waste away during the rainy season
Mm,
through September. And for a volcano experiment, it's great because you can go down there in July, August, September and put out sensors and reliably record small lahars coming down from the volcano, and we can do targeted experiments. So over the last 4 years, we've been working with colleagues at Insavume, an organization within Guatemala, to really try to improve the monitoring of these lahars using both seismic tools and infrasonic tools. And so that was all precipitated, I would say, by the discoveries at Villarrica, where, yes, indeed, not only is it interesting to study eruptive processes using infrasound, but surface flow activity can be tracked and quantified using infrasound technology.
Yeah, kind of a two for one.
Mhm.
So the infrasound signal for Lahar, I'm trying to picture this in my head because it's not a single pulse event like you just showed with the animated pressure waves at the summit. It's a protracted event, and so is it kind of like equal amplitude but long duration? And that's sort of the signal, and you'll see that at
Mhm.
whatever wherever the sensor is, it's going to see that as long as the Lahar's moving past the sensor.
Yes. Yeah. In fact, what we're looking at with Lahar infrasound is tremor-like signals. So
Mm,
I talked earlier about these explosion signals. The tremor is often lower in amplitude, but it's extended in duration. And what you need to do is put out multiple microphones. This is another conversation for another day, but many microphones put together can do wonders at trying to identify those Lahar signals, even when they're not very high amplitude, and identify where those sounds are coming from. And so one of our recent results demonstrated that we can even listen to these very small lahars from Fuego volcano when they're 5 kilometers away, 3 miles away.
wow.
The sounds are intense enough that we know something's coming our way.
Hmm.
Um, and so that's kind of exciting as an early warning forecasting tool.
So the infrasound is the actual energy transmitted through the air before as the Lahar comes down. So it is a bit of a predictive, or
Mhm.
it's ahead of the Lahar by how much? Like how much time? Like tens of minutes maybe, or less than that? I guess it depends on how far away you are too.
Yes. So at Fuego, which has smallish lahars, we have detections 5 kilometers away. And these lahars are not moving very fast. I said at Villarrica, they are trucking down at 38
Yeah,
meters per second.
right.
At Fuego, the slopes are lower. These are smaller events. And we actually can walk up to the edge of the drainages and set up cameras and see these things in real time. They're moving 10 meters per second,
Okay.
which is, 20 miles per hour.
Yeah, still
You, you don't
yeah,
you don't want to be in the drainage when they're coming your way.
right.
But they're actually I can find a video of that while we're talking. And
Can you figure out as you're looking for that? Can you figure out or estimate the volume of the Lahar based on the infrasound signal, or does it just say, "Hey, a Lahar's coming" or has been initiated, or does it actually give you some sense of the size and the volume?
um, yes, I think that there's a lot that you can do with the amplitudes of these Lahar signals. In fact, it's one of the things that we're really interested to try to do. Like, how big is the event that's coming our way?
Right.
Should we tell people, and you can do this with social media now, get out of the canyons. At Fuego, there is a very real hazard for people who have to cross these lahars to get to their communities.
Mm-hmm.
And also, there's people who are mining the gravel in the rivers. So it would be really nice if they could be warned that there's something that's
Yeah.
hazardous
Even
their
five
way.
minutes warning would be a huge thing, right?
Yeah. Um, and so, oh, I do have a lahar video that I can find. And yeah, nope, not that one. All right, here we go. I'll share my screen one more time.
Yep. Thank you.
Yeah. Yeah, this is just an example of a fairly small lahar that's coming down from Fuego, and these things are very common. I would say in this particular drainage, this is called Ceniza drainage.
Mm-hmm.
These events happen twice per week. Play it one more time since it's a short clip.
Yeah, kind of a wider like floodplain there, so less hazardous, but where it's more channelized and higher volume, they could be
Mhm.
much more dangerous.
Yeah, and this is the distal portion of the Lahar. Probably in another few kilometers, it's ground to a halt. There's no more flow.
Mm-hmm.
But it started up, 5 kilometers from the volcano where the loose ash and debris were collecting over the course of years, and then the rain event caused it to mobilize. And then, like I said, it's only moving 5 to 10 meters per second when it gets down to the flats. But this is
Right.
where people are, and this is where our monitoring infrastructure is.
Yeah, and it
So
doesn't take much water to lift your car or knock you off your feet or whatever. So
Or
Yeah,
destroy a road too. I mean, they rebuild these. There's roads that go straight across these Lahar paths, and they just have to bulldoze new paths, you
right.
know,
Every
every few
season.
weeks.
Yeah.
Um, but to answer your question, we can listen to a flow even of this size from several kilometers away, and that gives us 20 minutes of warning before it
Wow.
arrives
Yeah, that's
for the slow Lahars.
right. Is this similar to, like, I know on Rainier they have their Lahar detection system? I think the
Mhm.
verbiage I've heard is they have some sort of acoustic detectors. Is it actually infrasound they're using, or is it just sound but a different like set of
Mhm.
frequencies?
Yeah, that's a great point. One of the frustrations that I have is with the nomenclature of these different sensing devices. Uh, so Lahar detection has been done using seismic techniques for some time, very effectively. And the seismic tools are really good for figuring out when a flow is adjacent to the sensor. So if you put a sensor way up high in the volcano, it's going to tell you a Lahar is coming down.
Yeah, it just passed the sensor, just went back
Yeah.
past it. Yeah.
And those sensors have been called for historic reasons acoustic flow monitors,
That's the term I was looking for. Yeah.
AFM. And it's technically correct because it is a device called a seismometer or a geophone that's buried in the ground that's detecting the acoustic signals propagating through the ground. But we also like to use the word acoustics synonymously with sounds. So the AFM, which is the traditional tool, is actually a seismic tool. And then now, more recently, we're adding infrasound to the mix.
Mm.
And I'm going to just tell you that the two things together are really powerful. Always put out a seismometer next to your infrasound, and you have the whole picture. You have energy traveling through the earth as well as through the atmosphere, and together those two things are very powerful. Um, so, yeah,
So is the
both.
U? I'm assuming the USGS has embraced this technology, and are most of America's monitored volcanoes pretty wired with infrasound, or would you like to see them do more? And like, kind of, what's the status of that currently?
Thank you for asking that question. Yeah, the USGS is gotten behind infrasound wholeheartedly. And you mentioned Mount Rainier as a place where they are actively interested in monitoring Lahars. Have you done a show on Mount Rainier and its Lahars by chance?
No, not yet.
Yeah. Um, yeah, I can give you some names of people who would like to talk about
Oh, that'd
the
be great.
hazards
Yeah.
of Lahars. Uh, but suffice to say, it's the number one hazard from Mount Rainier, and it's the thing that perhaps the USGS worries about most. But the positive is that Lahars do move at a finite velocity. And so if you are able to identify them well upstream, you can get people out of harm's way.
Yeah, you got ample warning time. Yeah.
So the USGS is throwing everything they can at the problem, and they're doing really cool, innovative science by doing everything from AFM monitoring. They've recently become interested in implementing infrasound monitoring. They have cameras, they have tripwires. I think they're even using radars so that they
Wow. So
can,
they're throwing the whole kitchen sink at it basically in terms of instruments. Yeah.
yeah. And redundant monitoring is a good strategy. Like, hey, maybe the infrasound isn't working today because it's too noisy, but we've got these other backup tools. So
Yeah.
Um, they recognize the Lahars from Rainier as a huge problem, and they are doing a great job of installing infrastructure to provide early warnings.
Mm-hmm.
Um, and the work at Fuego is great because it's like a laboratory. You can go there and you can test out these sensors and figure out what the pros and cons of each technology is and how well they work.
Yeah, because you've got a volcano that's producing these on a pretty regular basis. They're mostly small scale. So yeah, it's
Mhm.
like the perfect kind of test facility for seeing how well the
Yeah. And
sensors
rain,
work.
really briefly, because you should talk to someone who is from the USGS on the subject of Rainier Lahars. But Rainier Lahars in the geologic past have been immense, really big destructive events, even though they don't have the monsoon style frequent Lahars that Fuego has. So
Right.
infrequent, very large events, whereas Fuego has a ton of a ton of lower magnitude Lahar events.
Well, probably just speaking to different triggers, right? The Fuego events are climate produced,
Hmm.
whereas the Rainier ones, I'm assuming, would be little hiccups and small minor eruptions underneath the glacier on the volcano, but releasing larger volumes of water.
Yeah. We call it secondary Lahars when they're triggered by rain events, and primary Lahars when they're triggered by an eruption
Okay.
or, yeah, something from the volcano. And the story of the Armero Columbia tragedy is a warning to us all that these large primary Lahars, I don't know if your
Yeah,
viewers
85, 30,000 people die, something like that. Just terrible.
and,
I mean, that was
and
really the catalyst for so much of what I think the USGS started doing with monitoring, the way I understand it, just historically.
yeah, and that was associated with an eruption, and there was quite a bit of lag between the eruption and when the mud flows reached the populated areas. So that's analogous to Mount Rainier's situation.
Right. Yeah. Just lots of time there. Wow. Fascinating stuff. Well, do you have any other little, I mean, I know you have like so many more aspects of your research you could probably talk about, but maybe a last story or experience or parting thoughts, anything you want to share before we wrap this up?
Yes, yes, I do. So I talked about Lahars and surface flows, and I just need to add that the infrasound technology is being utilized to monitor snow avalanches. I did mention that, but it's an ongoing project that Boise State has with departments of transportation all across the Intermountain West. I work with a local industry partner in Boise called Snowbound Solutions, and Scott Havens is head of operations there, and he's also an infrasound specialist. But we're monitoring snow avalanches in Utah and Alaska and California using this technology, and it's very useful and applied. So again, we like it when our science is applied.
Yeah. Well, and when it can
Uh,
be applied to so many different, phenomena.
mhm. And then beyond, surface flow activity, which is this whole field, we've been using infrasound to study earthquakes. And fortuitously, in 2020, we had a non-damaging earthquake in Stanley, Idaho, in an aftershock sequence
Mm-hmm.
that our group has been able to record and make sense of this world of low frequency sounds that are being produced by small earthquakes. And so we after that 2020 earthquake, the main shock, we scrambled to put out something like 18 sensors, microphones, and we recorded the sound wave field from hundreds, if not more than 1,000 earthquakes. And we can understand how sounds are produced by earthquakes. You may or may not know that because most people are sensitive to the ground shaking, but when the ground shakes, it shakes the atmosphere.
Right.
And we can either, sometimes you can hear earthquake sounds, but there's a world of infrasound produced by these earthquakes as well.
Yeah. So I mean, that almost opens up another can, but what does that look like when earthquakes generate infrasound activity? Um, is it like a clear signal? Is it kind of mixed? I mean, we're still having aftershocks from that 2020 earthquake in
Mhm.
Idaho. That aftershock sequence hasn't ended fully. They happen every week up there, low magnitude. So you're still detecting those, and like, what do you make sense of all that? That's got to be a chaotic pile of data.
Yeah, it's awesome data. You get an earthquake that happens, ground is rupturing, and it's complicated and awesome data. So it moves the ground all over the place. It might shake the ground near the epicenter, but it also can shake the ground. We think in the high mountain terrain, it tends to ring those big peaks like bells.
Yeah.
And so with the proper infrasound configuration, we can locate those sources and figure out what is shaking most. And so we can almost create these heat maps of sound production from a lot of earthquakes. And the signals are complicated, but we always put out multiple sensors at the same time, and they're capable of figuring out where the sounds are coming from.
And I imagine you need to like take the sound data and also tie in like the epicenter and the foci and like know exactly
Mhm.
where did the earthquake actually initiate, and then how was the sound dissipated from that quake. Does that reveal anything about how the or how the fault actually moved, like movement, and like, oh, it was moved, the direction of motion was maybe to the north or something like that? Can you pick that out from the infrasound?
I love these questions because they're things I'm thinking about just now. We have a proposal under consideration at the National Science Foundation to study that catalog of earthquakes from Stanley. Again, maybe 1,000 earthquakes, and some of them are associated with deep earthquakes, some are shallow earthquakes, some have normal faulting, some have strike slip
Mm-hmm.
faulting. And so one of our working hypotheses is that yes, you may create more sound from an earthquake that's shallow, large, and has this vertical sense of offset, like a normal event,
Mm-hmm.
a normal sense of motion. A strike slip earthquake may be less inclined towards moving the ground up and down and creating that
Yeah, so
vibration.
it'd have less of a signal with infrasound. That makes sense to me too. Just
Invite me back in a year or two, and when we have these results published, we'll be able to share what we've learned.
that
We'll
would
have
be
your answer.
No, that would be fantastic. Because I mean, I feel like we could keep going. We'll have to do more sessions for sure if you're up for it, Jeff. Because every topic is just like, definitely geophysics was not something I ever took coursework in. It's definitely not my skill set. But volcanoes I'm interested in, and as a structural geologist, I understand some of the earthquake parts of what we talked about. And so just this using this new tool to understand the dynamics has been really fascinating. So, well, thanks so
I'll say,
much. Yeah, go ahead.
whoa, sorry,
No, you're good.
2 more minutes.
Yeah.
I know that you have to go to lunch, but
No, you're good.
um, firstly, we just published another paper about not earthquake, not avalanche, not Lahar, but about the subject of fire infrasound. Okay, so it turns out that wildfires produce infrasound, and that we can record those infrasound signals and make sense of them. And so that has application for well, a growth industry in the Intermountain West, which is natural wildfires. So we're very excited about that new application of infrasound. And
Wow.
then, and as I use the word we, I want to end with a shout out to my people at Boise State.
Absolutely. Go ahead.
Can I do that?
Yeah, you bet.
Okay. So one of the reasons we've done all this research, and I think we've made a lot of progress in the field of infrasound science, is that we found a way to build low-cost infrasonic microphones that are calibrated scientific devices. It's been a long road since my graduate student days, but we have infrasound sensors that we provide to the community that are produced in-house at Boise State University. And they're low cost, meaning we can put together a lot of these instruments for targeted deployments and experiments. And I couldn't do this without the help from a ton of people at Boise State University. So I want to give credit first and foremost to Jerry Mock, my lab manager, who is a former Boise State University master's student. I also want to give credit to Jake Anderson, who's a research professor in our group, and he's doing incredible things with infrasound instrumentation. Um, Owen Walsh is another graduate student, current graduate student, who is both a geophysicist and an engineer. So those two skills together
Yeah.
are hugely important for us.
Yeah.
And then I'll leave it there. But man, there's so many undergraduates and graduate students and a community of people in our infrasound lab over the years that have made all this work possible. And so, yeah, I'll end on that note
Yeah. No, I
because
mean, it seems like you built a great community of researchers and colleagues that are and students that are working with you on this infrasound thing, and I'm excited to see where it's going to go because I mean, one after another, all these applications you've just laid out here. I mean, and who knows where we might take it in the next 5-10 years. It's really incredible. So awesome. Well, thanks so much for spending time with us today, Jeff. Stick around after I close the show here, and we'll chat for a few more minutes, and then I'll let you go. But appreciate your time today. We loved hearing about how you're using your research to further our understanding of volcanoes and other phenomena. Just couldn't be more appreciative of your time. So thanks again.
yeah, well, thank you for your interest. The subject is obviously something that I like to talk about. So you gave me a platform to share. I
No,
appreciate that.
no, happy to do so. Thanks so much.
Bye bye.